Let's imagine we have two local programs that need to communicate data between each other. Program A needs Program B to manipulate some data for it, but be able to retrieve the processed data once Program B is done. Inter-process communication, also known as IPC, is a mechanism that allows the transfer of data between processes. There are two common methods for IPC: shared memory and message passing. The latter I'll save for another video. In the shared memory method, a region of memory that is shared by cooperating processes is established. Processes can then exchange information between each other by reading and writing to the shared region of memory. Shared memory can be a useful tool in a programmer's toolbox. For example, imagine you need to share some data between your application and the kernel, or you need to transform some data but can only do it via multiprocessing. For the purpose of this video, let's write a small program that can still demonstrate these concepts. Our program will initiate some shared region of memory and write an unsorted array of integers to it. It will then fork a new child process to manipulate, or sort in this instance, the array on its behalf. Now it's important to note that the code we're writing today will only work on POSIX compatible systems. There are alternatives to the functions we're using that will allow shared memory on Windows and other non-POSIX systems, but they're not the focus of today's video. So with that out of the way, we'll start by importing OS, FS, mem, and C, as well as creating a standard out writer. We'll also create an unsorted array of integers. This is the array that we want to write to shared memory and have the child sort on our behalf. There's three things we need to consider when creating our shared memory region: who needs to access it, how long will it need to live for, and what memory synchronization methods are necessary. In the case of the application we're building today, due to its simplicity, we won't have to worry about memory synchronization. So who needs access to the region of memory? Well, the parent and the child both will need access to it, as they're both manipulating the data within the region. Because both of these will be contained in the main program, a pointer to the shared memory region will be mapped to a variable both the parent and child can access. If the programs were separate, we would need to give the shared memory region a name which both can call back to in order to access. The second question was, what is the lifetime of our shared memory region? Well, the lifetime of a shared memory region is bound to the process owning the memory. The region of memory we plan to use only needs to live as long as the parent program does. This means that we can let the operating system provide a new, uninitialized anonymous mapping not associated with any file on disk. If we do need the shared memory region to live longer than our program, we can map it to a file. These questions are important as they'll affect how we create our region of shared memory later. With our needs planned out, let's go ahead and create a region of shared memory using the mmap syscall. Zig provides the binding for this via the mmap function. This function takes in 6 parameters and returns a pointer to the region of shared memory. The first parameter is a pointer to the location in memory of where the shared region should start. By passing null to this, we allow the operating system to choose the starting address for the mapping. The second parameter specifies the length of the memory mapping. It indicates how many bytes we want to map into the address space. Using the built-in sizeof function, we can set this to the size of our array in bytes. The third is a series of protection flags. In our use case, both the parent and the child will need to read and write to the region of shared memory. We can allow this by ORing the flags protection read and protection write together. The fourth parameter is a series of other flags used for configuration. We want this region of memory to be shareable, so we'll set the map shared flag. As described before, we don't want this memory backed by a file, so we'll also set the map anonymous flag. The fifth parameter is a file descriptor. If we were mapping this shared region to a file, this is where you would specify the file's handle. Because we aren't using a file, we'll pass -1. The final parameter is used when creating a mapping for a file-backed region. It specifies the offset within the file from which the mapping should start. We'll pass 0 to this. Although our program only needs an anonymous mapping, let's take a short detour into how we would map this region to a file. We would first need to create a file, truncate it, and once done with the memory, unlink the name. The preferred way of doing so is to call shared memory open, ftruncate, and shared memory unlink. Unfortunately, Zig doesn't have its own implementation of these functions. This means there's 3 ways to tackle the problem. Either use the libc functions directly, maintaining a very C-like style, build a Zig wrapper around the libc functions, or write wrappers around the system calls directly. Let's take a look at how this would be done using shared memory open as the example function. If our application is able to be linked with libc, we can simply build a wrapper around Zig's libc binding for shared memory open. Because we're building a wrapper, we can also add Zig-style error handling to the C-style functions. Shared memory open returns -1 if it fails and writes the error code into the global error_no variable. We can obtain this in Zig using the getErrorNo function, switch on the result and return specific errors based on the result. With the wrapper built, we could use it like so. In this example, we've only built a wrapper around shared memory open, so ftruncate and shared memory unlink are being used directly from libc. We first create and open a file using the shared memory open wrapper we just built, remembering to unlink the name once done. Using ftruncate, we can truncate the file to the correct length to hold our mapped memory. Finally, when calling mmap, we pass in the file descriptor for argument 5 instead of -1. However, if your application isn't able to link with libc, you'll need to write your own implementation of the desired function. Taking a look at how libc defines shared memory open, we can see that all it's doing under the hood is calling the open syscall with a few extra checks. Here's an example implementation of shared memory open in Zig, not linking with libc and instead using the Linux open syscall. Feel free to pause the video to take a deeper look. Going back to our original example, just as we created the mapped region, we must also remember to unmap it once done. Let's defer its teardown using the mmap function. Mmap simply unmaps a region of memory. With our region created, let's write the array of numbers to it. We can do so by directly writing to the pointer. The fork syscall will create a new process by duplicating the calling process. After calling fork, we'll have two separate, nearly identical programs running the same code with the same values in memory. Fork returns the PID of the calling process. This will be 0 for the child and a non-zero, non-negative number for the parent. Zig provides us a direct way of calling fork via a wrapper. Something to note here is that if we wanted this section to be Windows compatible, we could instead call the system agnostic method spawn, which on Windows will return a H process, while on POSIX will return a PID. Since we have only been building this program with POSIX in mind, we'll continue to use the POSIX variation of the function. Calling fork, we can obtain the PID and, using an if statement, branch main off to handle the two processes. Because the shared region of memory holds our numbers array and is of the exact same length, we can sort it in place. Since there's nothing else we need the child process to do, we can simply exit. The parent should wait for the child process to finish executing before it continues with its own execution. The wait PID syscall will suspend the current executing process until the specified process terminates. We can use Zig's wrapper function wait PID, passing in the PID obtained from the call to fork. Wait PID will return the status code the child exits with. This can be used for error handling purposes. With the shared memory region pointing to an array of integers, we can loop over the region and print out each number. I'll also add the same statement before processing the array so we can see the array pre-sorted and sorted side by side. Running the code, we can see that our program successfully maps a region of shared memory, spawns a child to sort the array, and then reads it back to the user. You can find the code along with further resources used during the making of this video in the description. If you have any questions, feel free to leave them in the comment section, as well as liking and subscribing if you enjoyed the video. Thanks for watching.